Hey guys, let's do another orbits question for gravitational fields. Scientists wish to place a geosynchronous satellite near a moon at an altitude of 415 kilometers. The mass of the moon is 7.63 times 10 to the 22 kilograms, and it has a radius of 1.47 times 10 to the 6 meters. Calculate the velocity and period of the satellite. So let's just get familiar with some terminology in this question. First things first, geosynchronous means it has an orbit and it has a period of orbit similar to that of the host planet it's orbiting. If this was the Earth, an example of a geosynchronous satellite would be the moon, because the same side always faces the Earth. In this case, we're not dealing with the Earth, we're dealing with another moon of some other planet. Okay. Otherwise, of course, we could just figure out the period in a different way. So let's start off this problem by drawing a picture. We've got the moon, and nearby we've got a satellite. Now the question tells us that the satellite is at an altitude of 415 kilometers from the surface of the moon. So this distance right here, we can call it D, is 415 kilometers. We're also told the radius of the moon, it's 1.47 times 10 to the 6 meters. So that's the distance from here to here. So clearly this diagram isn't to scale, but that's okay. So this R is 1.47 times 10 to the 6 meters. Okay, why don't we just call this R sub m because it's the radius of the moon. We're also told the mass of this moon. It's 7.63 times 10 to the 22 kilograms. Now, whenever we do these kinds of problems, something you need to know is we always deal with force of gravity or even centripetal force as the distance between the center of the two objects. So, in other words, the distance from here to here. But we're not given this distance in the problem directly. We're given a way to find it, which is why it's always a good idea to draw a picture, because if you had just plugged in 415 for the distance between them, you wouldn't get the right answer. You need to add the 415 kilometers to the radius of the moon. Now, I want to first make sure these two are in the same units, so convert 415 kilometers to meters by multiplying by 1,000. So 415,000 meters. Now this distance I'll call RMS, the distance between the moon and the satellite. So RMS is equal to RM plus D. And when you crunch that out, when you add 415,000 plus 1.47 times 10 to the 6, you are going to get 1.885 times 10 to the 6 meters. Okay. So now let's move on to what the question is asking us for. We're asked to calculate the velocity and period of the satellite. So we're looking for V and T. So I'm going to start off this problem with an equality statement of the centripetal force is equal to the force of gravity. Because in this case, the fact that the satellite is moving in a circular motion around the planet or around the moon is due to the force of gravity. So centripetal force is mv squared over r. The mass you put here is the mass of the satellite, the thing that's orbiting the host object. Okay. And this distance r is the distance between the center of each mass, so RMS. Now force of gravity is G m1 m2 over r squared. Now the r again is RMS. One mass is the mass of the satellite and the other is the mass of the moon. So we can now do some canceling. One RMS on this side cancels out with one of them on this side, and the masses of the satellite cancel out. So we're left with V squared equals G mass of the moon divided by the distance between their centers. So if I want to solve for V, I simply have to take the square root of G mm over RMS. Okay, so at this point I can just plug in my values. Okay, so G is a constant, you can just plug it in. It's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Okay, the mass of the moon is given to us on the problem. It's 7.63 times 10 to the 22 kilograms. And we're dividing it by the distance between their centers, 1.885 times 10 to the 6 meters. And make sure you don't square it because we canceled out the square up here. Okay, so at this point, you just have to be careful not to make any errors as you punch it in your calculator. But if you do everything correctly, you should be getting a speed of about 1.643 times 10 to the 3 meters per second. Okay, so there's the velocity for the satellite. Now, if we wanted to find the period of the satellite, the time it takes for it to make one complete orbit, I'm going to go back to my standard definition of speed. And speed, I know, is equal to distance over time. The distance that the satellite undergoes is the circumference of that circular orbit, or 2 pi r. And the time for it to go into one full orbit is called the period, right? So capital T. So V is equal to 2 pi r over T. I know V, I know R, I need T. So essentially what's going to happen is you're multiplying both sides by T, dividing both sides by V. Or seen another way, T and V are simply going to swap places, okay, because they're across the equal sign. So T is equal to 2 pi r over V. So let's plug in those values. So 2 pi, I just found, well, R is actually given to us, right? The 1.885 times 10 to the 6. And V we know from here, so we just plug in those numbers. And then divide by V. 1.643 times 10 to the 3 meters per second. So crunch those numbers and you are going to get a period of 7.209 times 10 to the 3 seconds. Okay, so that's it for this video, guys. I hope you enjoyed it. Be sure to subscribe to Physics in the Flesh so you never miss videos from me. I post every weekday at 12 noon. So please stay tuned tomorrow for video 150, Coulomb's Law 1. Alright guys, that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button so I know what I'm doing makes sense to you guys. And you know how you can stay tuned for my latest videos? By subscribing to Physics in the Flesh. I post every weekday at 12 noon, and this way you guys can always be the first to know when I post a new video. As always, guys, thank you so much for watching. If you missed any of my earlier videos, be sure to click over there on the right. You can click and watch those videos on your screen right now. Anyways, guys, Physics in the Flesh out. Woo-hoo! Holy crap, my nose looks big on camera. I gotta find a new angle.